Okay, so in the last video we talked about how the speed, that is the average speed of a given gas molecule, is directly proportional to the temperature, that is the kinetic energy is a measure of the average, the temperature is a measure of the average kinetic energy of a given gas molecule. And so, and what we also saw was that as the mass of our gas molecules increases at the same kinetic energy, the velocity will decrease. And this is related to our equation for velocity or kinetic energy, right? Kinetic energy is 1/2 times the mass times the square of the velocity. So if kinetic energy is constant, the and the mass increases, the velocity must go down. So lighter molecules will be moving more quickly, and heavier molecules will have a lower average speed. Okay, we saw the distribution of speeds. So we can describe the root mean square velocity as a way of describing the average velocity of gas molecules using this equation. U, representing the root mean square velocity, is equal to 3 times the gas constant R times the Kelvin temperature over the molar mass, and taking the square root of this whole thing. Now, when we use this equation, we are forced to use our SI system of units, which uses a different value of R than we've used up until this point. So the value of R we are going to use is 8.3145 joules per mole Kelvin. And the reason we are using this is that in the SI system, 1 joule is equal to 1 kilogram meters squared per second squared. And that's really the definition of a joule. We define the joule as 1 kilogram meter squared per second squared. And we see that when we take the square root of these two, we take the square root of this, we're going to end up with meters per second in this equation. Now, because we define R in this way, that means when we are describing the molar mass, so we're going to use R as 8.3145 joules per mole Kelvin. Temperature must therefore be in kelvins, and the molar mass, which typically we've used as grams per mole, we need to convert this to kilograms per mole when we calculate root mean square velocities. Again, it's simply using the SI system for our value of R. So let's do a couple of quick examples here. So let me make a little bit more space here. Okay. So for example, if we have helium at 300 kelvins temperature, okay, we can determine the average speed, that is the root mean square velocity, simply by taking into account the temperature and the molar mass. So here, M for helium, if we look in our periodic table, is about 4. It's 4.0, let's see what it is exactly, 4.003. This would be grams per mole. Okay. Now again, in our SI system, our masses need to be in kilograms. So 4 grams is equal to 4 times 10 to the minus 3 kilograms. So we have 4.003 times 10 to the minus 3 kilograms per mole. Okay. Here our temperature is 300 Kelvin, and so now the root mean square velocity is simply the square root of 3 times our value of R, 8.3145 kilogram meters squared per second squared, times our Kelvin temperature, 300 Kelvin, divided by our molar mass in kilograms per mole. So, I think I forgot my units here. Let's correct these. So this is kilograms per meter squared per second squared per mole Kelvin. Okay, then times 300 kelvins divided by our molar mass, 4.003 times 10 to the minus 3 kilograms per mole. So now when we're using when we're using these units, I need to make a little bit more space for us here. When we're using these units, we see that our kilograms will cancel here. Our moles, up here we have inverse moles, down here we have inverse moles, so those cancel. Our kelvins cancel, and we're left with units within our square root of meters squared per second squared. So when we take the square root of this, the units we will get are the units for speed, namely meters per second. So now when we do our calculation, we take 3 times 8.3145 kilograms meters squared per second squared per mole Kelvin times 300 kelvins divided by 4.003 times 10 to the minus third. That will give us some very large number, and we will take the square root of that number, and that will tell us that the root mean square velocity of a helium molecule, of a sample of helium, is 1367 meters per second. Okay, so this is, helium molecules are moving very rapidly. Now let's compare this to some other type of gas. So let's stick with our noble gases. Okay, let's say instead of talking about helium, we are talking about krypton. Okay, so we're going to repeat this calculation for krypton. Okay, here the only thing that changes in this expression is going to be our molar mass, right? A little bit more space here. So for krypton at 300 kelvins, we still have the same equation. Move this down here. I'm going to just copy this whole thing, in fact. Let's copy that and move it on down here. So for krypton at 300 kelvins, the only thing that changes here is this value. Okay, and we look in our periodic table, and we see that krypton has a molar mass of 83.80, if my eyes are correct. 83.80, and that's grams per mole. So in kilograms, that would be 83.80 times 10 to the minus 3 kilograms per mole. And so our units cancel just as they have before, and we repeat our calculation. 3 times 8.3145 times 300 divided by 83.8 times 10 to the minus 3. And then we take the square root of that number. And so for krypton at 300 Kelvin, now our velocity, or root mean squared velocity, is 299 meters per second. So we see what a dramatic difference in speed we have between a sample of krypton versus the 1300 meters per second for a sample of helium. So the helium molecules, because they're so much smaller, at the same kinetic energy, that is the same temperature, they are moving much more rapidly. Okay, so what we need to remember when we're doing these calculations is, first of all, we are using the SI system of units, that is 8.314 joules per mole Kelvin for our value of R, our ideal gas constant. We of course must use the Kelvin temperature, and when we use the molar mass of our gas, we must express this molar mass in kilograms per mole rather than the more familiar grams per mole.